and we are going to go through some tutorial questions. The topic for this week is about planar kinetics of a rigid body. We are going to look at the principle of work and energy, and also at the conservation of energy. The principle of work and energy always applies. Okay? Whereas the conservation of energy would apply only when we have conservative forces. Now we are going to go through a number of questions which would clarify how and when we get to apply the principle of work and energy, which is at all times applicable, and then how we are going to apply the conservation of energy when applicable. Let's get started. We've got the first question. We've got a bar, a 50 kilograms bar falling from rest, and we need to find the speed of its end B before it strikes the ground. So notice the rod, the bar AB is pinned at A, its length is 2 meters, and it is going to fall clockwise until the end B hits the ground. Obviously, we need to consider the free body diagram. So we need to sketch the free body diagram. It is shown in here. So I would have an AX and an AY. I would also have the weight of the bar. The weight is 50 times 9.81. AX and AY are mainly variables. And then for my kinetic diagram, from point G, which is the centroid of my bar, I would have VG clockwise. W is clockwise, the angular velocity. Let's note the principle of work and energy. T1 plus sum of work done from 1 to 2 is equal to T2. That's mainly the principal equation. So T is the energy done from the initial state to the T2, which is the energy done at the final state. That's the kinetic energy. And sum of U from 1 to 2 is the sum of the work done from 1 to 2. Now let's look at how each of these we can find or represent. So T is actually, in this case, half mvg square plus half ig omega square. Okay. So in this case, my Vg is R omega and my Ig is 1 over 12 ml square. Now notice, because in my initial state, omega is 0. So it is starting from rest. So omega 1 is 0. And notice that T, in this case, is going to be notice Vg is R omega, R is L over 2, so this is going to be L over 2 omega. L over 2 times omega. So in this case, my T1 is going to be 0, because omega 1 is 0. Now what about my T2? T2 is Ig plus half mvg squared. So this is going to be half times m all right, let's leave this one, T2, for a second. Okay. So T2 is half Ia omega 2 square. Now, how did Ia come into play? We are going to prove it soon, okay? And that is, I'm going to show you how its demonstration is. By looking quickly in here, look at this bit. T is half of Ia omega squared, okay? Where Ia is Ig plus m times R squared. Now, what we need to do is to sub in the values. So I need to find Ia. I need to find omega 2 is my variable. And now Ia is Ig Ia is Ig plus m L over 2 square. Okay? Bear in mind, Ig is 1 over 12 ml squared. Now all of this would give me that T2 is 33.3 omega 2 squared. So if I was to sub in here for T2, T1 is 0, T2 is this value. Now I need to find sum of work done from 1 to 2. Okay? Now, sum of the work done from 1 to 2, what work do we have? We only have the work done by the weight of the bar. And to find that, it has this formula. U of the weight is negative W delta Y, where W is the weight, which is 490.5. So negative 50 times 9.81 times delta Y. Delta Y is Y2 minus Y1. Okay? Delta Y is Y2 minus Y1. Now, what is Y2? Y2, in this case, is the location of G with respect to my datum. If I consider my datum A, then when the bar hits the ground, this is going to be G2, A. So Y2 is 0. And Y1 is the location, the initial location. So if this is my datum, then Y1 is the position of G with respect to my datum, which is 1 meters. So 0 minus 1. So here I would have minus 1. And then this would be 490.5 Newton meters. Now, I get to apply the equation. So I'm going to show you now the solution because we are running out of space in this one. Okay. I want to delete all of these ones. Sam, are you good?
That's right with me.
Yeah.
All right.
What is the solution? Free body diagram and the kinetic diagram. The main equation, T1 plus sum of work is equal to T2. Notice T1 is 0, T2 is 33.3 omega 2 squared. And then finding the sum of the work done minus W delta Y, and then finally we sub in the values we find in the main equation and we find omega 2. And once we find omega 2, it is R omega 2, VB is R omega 2, so we find VB. I'll leave it with you for a couple of minutes. It's not difficult. All we need to do is to decide on the equation, know how much is T1 and T2, look at what forces are doing work. Just keep in mind, work is force times distance. A force has to move, has to change location for work to happen. And then we apply this work and energy principle to find omega 2, which is our variable, and then we find VB. Any questions for me, Sam?
No, that's all pretty clear.
You're good? All right.
Yeah.
All right. So the topic for today is mainly very similar to this. So let's
Yeah.
look at the next question.
Cool.